Hello and welcome to the chemistry class. Today's topic of discussion is solid state, the structures and properties related to solid state. So we first start with the three states of matter. Well, matter exists mainly as three states. We know that gas and liquid particles enjoy more freedom than particles of solid. Strong attractive force hold these particles together in fixed places. They occupy definite positions and vibrate around a mean position. That is why we can say that solids are rigid, incompressible, and have definite shape and volume. Okay, now these solids can be classified into two broad categories. One is crystalline solid and another amorphous solid. Crystalline solids have definite geometric shapes such as this quartz crystal. On the other hand, amorphous solids do not have such regular shape, like this microscopic image of glass surface, resolution 50 micrometer. You see here, you will be surprised to know that both quartz and glass are chemically the same compound, that is silicate polymers comprising of silicon and oxygen atoms. The red balls are silicons and the blue balls are oxygen atoms. The only difference between the internal structure of quartz and glass is that quartz has a definite geometric pattern, or we can say a long range order of arrangement of particles, which is missing in case of glass. Look here, some ordered arrangements are shown here, but that arrangement does not proceed too far, that is they are short range order only. Okay, so that is one basic difference between crystalline and amorphous solid. One more difference between crystalline and amorphous solid is that crystalline solids shows anisotropicity. Crystalline solids are anisotropic. What does that mean? Anisotropicity means that crystalline solids have some regular arrangement of particles inside crystal. You see here the regular arrangement of particles. They will look different from different directions. If we see here, suppose like if you are looking at this crystal from this direction and you spin this crystal, you are spinning this crystal gradually, you will see the patterns are changing, isn't it? The patterns are changing. Okay, so that is why they are looking different from different angles. They are different positions from different directions, and this also matters about their properties. Certain properties like electrical resistance, electrical conductivity, mechanical strength, or you can say refractive indexes. So all these properties, when measured from different directions, can yield different values. Okay, so this is anisotropicity. This was not observed. This is not observed in case of amorphous solids. Amorphous solids have more or less same arrangement of atoms, similar arrangement of atoms along different directions, because there is no definite pattern involved in case of amorphous solid. an average pattern follows over different directions. So average value of physical properties will be observed from different direction, and all those values will be similar, which will be not observed in case of some crystalline entity. For example, the piezoelectric effect we can see here, that on elongation or on compression, the electrical conductivity changes to some extent, and the directions that involved in the measurement of electrical conductivity shows us that the values will be different in different directions. Okay, so this is what is anisotropicity. Crystalline solids can be classified into four broad categories: ionic, network, metallic, or molecular crystalline solids. Ionic solids, we know, are comprised of cations and anions. For example, the rock salt or table salt, sodium chloride, sodium cation and chloride anion. This one is sodium cation and this one is chloride anion. And we know that in ionic crystals, cations are surrounded by anions and anions are surrounded by cations. By this way, no two cations come in close contact with each other, or no two anions come in close contact with each other. Electrostatic attractive force operates between positive and negative charge that holds the ionic solid together. But when we take a piece of ionic solid and we can hammer, or we can put some mechanical stress over it, one part of ionic solid can slip past over another part of ionic solid, and then two positive ion will come close in contact with each other, and two negative ions will come close in contact with each other, and that is why some repulsion will take place, and that repulsion can break the crystals apart. The crystal will be broken, and this explains the brittleness of ionic solids. The next one is network solid. Like ionic bonds are involved in ionic solids, covalent bonds creates covalent solids or network solids, sometimes called giant solids also. An example is graphite, which is an allotrope of carbon. The next one is metallic crystalline solid. We have learnt metallic bond in class 11, and we know that in metallic crystalline solids, metal cations float over electronic sea of electrons. Look, these electrons, they are mobile electrons. The small particles are electrons, and these fixed spheres are metallic cations. Metal atoms share one or more electron and becomes metal cation, and those shared electrons are mobile electrons, which are responsible for thermal or electrical conductivity of metals. We know that metals are highly conductive, either thermal or electrical. The last one is molecular solid. Molecular solid is composed of molecules. Now molecules can be polar, they can be non-polar, or